Hey, Math 110 students, you might notice me in a different environment today. I'm in the sunroom at my mother's house because she broke her femur. So I am working from a new office today, and we're going to attempt to record our chapter 4.3 video on exponential functions. So let's see if we can do it. We'll just jump right in to our PowerPoint here. And we are in exponential functions. Nope, not that one. We are in here. All right. Exponential functions. And we are going to just first talk about what exponential functions even are. How do we find these on a calculator? Let's say you want to use a calculator to evaluate these. Not terrible at all. Let's do 3 to the 1.7 power. Find that 3 to the 1.73 power, 3 to the 1.732 power. These are approximations of 3 to the square root of 3 power, but we can do all of these. And let me just show you right here on my calculator. That works. All right, we're doing 3, okay? And then to get some odd exponent, not squared, there's the caret button. I think we said 3 to the 1.7 power. All right, and then we did a couple more, 3 to the 1.73, 3 to the, a couple other things, 3 to the root of 3, second, the root is above the square root button, root 3. Okay, and these get to be closer and closer approximations to 3 to the square root of 3. But it's very easy to find these on your graphing calculator. And if you wanted to round it to the nearest tenth, it would be 6.7. If you wanted to round it to the nearest hundredth, it would be 6.70. If you wanted to round it the nearest thousandths, it would be 6.705 because the 9 would make you round up. All right. Okay, back to PowerPoint. So that was not anything too hard there. Right, how about the laws of exponents? You remember the rules for exponents, that if we have exponents with the same base and we're multiplying them, we're going to add the exponents. If you raise a power to a power, you're going to multiply your exponents. You have to distribute the exponent if things are multiplied together. A negative exponent means it's 1 over that number to the positive exponent, and any number to the 0 power is 1. So let's just do a few of these and make sure we're comfortable with all of this. Okay, we'll do some basic ones here. Okay, how about 2 to the second times 2 to the third? All right, the rule if you're multiplying exponents with the same base is to add your exponents, and this makes sense. This is 2 times 2 times 2 to the third is 2 times 2 times 2, and that's for a total of 2 to the fifth. So the rule is you add the exponents. If you are dividing these guys, let's say 2 to the fifth divided by 2 to the second, then you are going to subtract the exponents. Now this only works if you have the same base. So this is 2 to the 5 minus 2, which is 2 to the third. Okay. If you raise an exponent to another exponent, okay, this is 3 to the second raised to the fifth, you multiply. This is 3 to the 2 times 5. This is 3 to the 10th power, okay? Or if you had 2x raised to the third power, you raise both parts to the third power. This is 2 to the third power, x to the third power, or 8x cubed, okay? One more. Let's do it something to the negative power. 3 to the negative 2 power. The negative means to put it in the opposite. If it's in the numerator, put it in the denominator. If it's in the denominator, put it in the numerator. This would be 1 over 3 to the second power, or 1/9. Okay? Laws of exponents. Hopefully you saw that in Algebra 1, but if not, we just had our quick review. All right, going back to our PowerPoint screen then. We're going to deal today with exponential functions. Exponential functions. And the big idea on exponential functions is that they grow at a different rate than linear functions. Linear functions grow at a fixed rate, but exponential functions grow at an exponential rate. And one of the main ways to tell these apart is looking at their slope. Okay, looking at the slope. All right, so let's say I gave you a set of ordered pairs here for letter A and a set of ordered pairs here for letter B. So the point -1, 6, 0, 2, 1, -2, 2, -6, 3, -10. Let's just look at this first set here. Okay, -1, 6, 0, 2. I'm going to write these down, and maybe you would like to write them down as well. So pause it real quick and write these down. Okay, did you get them written down? All right, let me switch to my camera here. And let's look at these guys real quick. All right, here they are. All right, so this is a set of ordered pairs. And what they suggest that we do is find the slope between them. And if the slope is the same, we know it is a linear function. If it's not, then we know it's a different type of function. Okay, let's just find the slope here between -1, 6 and 0, 2. Remember, for slope, you subtract your y values up top, so 6 minus 2 up top, and you subtract your x values on the bottom, so -1 minus 0. So I got 4 over -1, so I have a slope of -4 between these two. Okay, now let's go to the next two. Okay, now from 0, 2 to 1, -2, what's my slope? 2 minus -2 up top, 0 minus 1 on the bottom. Look, I once again get 4 over -1. I get a slope of -4. All right, let's keep doing it. All right, how about -2 minus -6 all over 1 minus 2? Is it 6 minus 2 is 4? 2 minus -2 is, all right, how about -2? Oh, yep. This is going to be 4 over -1. All right, look, every time my slope is the same, I have a constant slope. This first one is a straight line. Okay. First one is a straight line. So if I plotted those points on my graphing calculator, which I can do, one way you can do them is here on the, let's see, stats. Let's edit our list. So we had -1. Let's see, do I need to brighten this up so you can see a little bit better? All right, we had -1, 6. Oops. Let's see. All right, actually, I'm gonna clear this one off. Clear. Wait a second. Yeah, clear, delete. How do I? Oh, I did. Good. All right, now let's go over here and let's delete this guy. All right, good. All right, so now my x values are -1, 0, 1, 2, and 3. And then my corresponding y values were 6, 2, -2, -6, and -10. And let's plot plot one, and let's just do dots. Yeah, okay, we'll turn that one on. All right, and now let's just graph it. What? Uh-oh, what did I do wrong? L1, oh, L1 and L3. Okay. So step on L1. I should have done it L1, and my Y's I didn't realize were in L3. All right, now let's grab that. All right, and you can kind of see it. Just they fall right in a straight line, right? They fell right in a straight line. All right, that was a straight line. The slope was consistent everywhere there. Now, in our second set of data, I'll let you take a moment and write down the second set of data. You can pause me real quick. All right, did you get those written down? All right, I did. And I want us to look real quick at the slope between a few of these. We don't have to do all of them, but we'll find pretty quick. If I just found the slope between -181 and 0.27, That's going to be 81 minus 27 up top and negative 1 minus 0 on the bottom. What's 81 minus 27? That is 54 over negative 1. So I got a slope of negative 54. Okay. Now let's do the next 2 points. 27 minus 9 over 0 minus 1. That's going to be 18 over negative 1. Well, right off the bat, I see I do not have a straight line. There have different slopes between point to point. And if I showed you that on the graphing calculator, I've plotted these points, you actually see they do not fall into a straight line. They fall into what is a shape we're going to learn is an exponential shape. These are exponential functions. All right. So what are exponential functions then? All right. When we graph exponential functions, they grow at what we call an exponential rate. These are things that don't grow at a steady rate. They either get faster, they get higher faster, or they get lower faster. All right, so let's say 3 to the x, domain is all real numbers. And let's say we put in negative 10. Well, if you put in 3 to the negative 10th power, you're going to get a tiny little number. What about 3 to the negative 3 power? 3 to the negative 3 power. Let me show you how to put that in on the calculator. 3 to the negative 3. Again, we're going to use this little caret button right here. So let's quit out of our graph. 3 to the negative 3. Okay. And I get a decimal. If you want it as a fraction, hit the math button and choose number 1, fraction. It's 1/27. Okay. 1/27. All right, which is still pretty small. All right. And negative 2, negative 1. Remember, a negative exponent puts the 3 in the denominator. So these end up being fractions. Any number to the 0 power, so 3 to the 0 power is 1. 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. Keep on going. You're actually getting really big really fast. You start small, never get to 0. Notice that you just get infinitely closer to 0. So 3 to the negative 100 is infinitely close to 0, but it doesn't equal 0. All right, and so we get a graph that looks like this. It's going to get infinitely smaller, but it actually never equals 0 as you go in the negative infinity direction. But in the positive infinity direction, it's getting infinitely larger, faster. Okay. The general property, if you are taking, and notice what makes it an exponential function is that the variable, the x, is in the exponent. Okay, so 3 to the x, 2 to the x, 5 to the x, 1/5 to the x. The variable is in the exponent. Now, if you have a base, this is your base of your exponent. The a value is your base. If your a is not fractional, if it's greater than 1, then it's going to get higher left to right. No, excuse me, it's going to get 3 to the 1, 3 to the 2. Yeah, it's going to get higher left to right. Domain is all real numbers, but the range is going to be 0 to infinity. Okay. And this is what it'll look like if your a value is greater than 1. Okay, so you'll never be down in the negative y's. Okay, you'll always be in the positive y's if your a is greater than 1. Now, if you have a fractional, so between 0 and 1 base, here 1/3 is the base, x is the exponent, then it's going to go in the other direction. It's going to get infinitely smaller. The larger the x values, it's going to go down left to right. Okay, the base is a fraction, the exponent is the variable, and this one gets infinitely smaller left to right. Still, the domain is all real numbers. You can put in any x value, but notice that the range, the y values you get out are all positive. Okay. All right, there you go. All right, now we can use transformations on these guys just like we would with quadratics or cubic functions or square root functions. The basic one for 3 to the negative x plus 1 would just be 3 to the x. So think about 3 to the x, which we found just a little while ago. All right, here's the graph of 3 to the x when x is 0, y is 1, when x is 1, y is 3, when x is 2, y is 9. When x is negative 1, 3 to the negative 1 power is 1/3, and you get this graph here. Now, first, what does the negative x do? Well, the negative x is going to flip it around the y-axis, and the positive 1 will pick up the entire thing and move it up 1 unit on the y. All right, so we're going to reflect around the y-axis. Okay, here we go. And then we're going to shift everything up 1 unit. So from 0, 1, 0, 2. Instead of negative 1, 3, we'll have negative 1, 4. Okay, so transformations work on these guys in the same way. Now our new domain, our range, our domain is still all real numbers. And still put in any x you want, but our range changed. Now our range is from 1 to infinity, not including 1, but 1, it will get infinitely closer to y equal to 1 without crossing it. All right, another interesting number in the exponential world, and we'll be using it a lot in the chapter, is number e. Number e is very, very similar to pi. All right, think about pi. We use a symbol to represent pi. It's an irrational number, 3.1415, blah, blah, blah. Okay, it's a number, but why do we deal with pi like that? Why do we even care about pi? Because it shows up a lot in real life. So we have this irrational number that you can't fully write out that shows up in real life all the time. And so we develop a symbol to represent it so we know what we're talking about. Well, here's another one, E. E shows up particularly in financial applications. E shows up a lot. And so we have also developed a symbol for E. Euler's number is what, where we got it from. Kudos to Euler for figuring it out the first time. Okay, Euler's number. And that we represent it with the letter E, and it's roughly 2.7. In fact, let me show you on my calculator. If you want to see a close approximation of E, then just go over here to E. Okay, where's E? Well, there's E to the X, but here's right above the division symbol. It's just little old E. And to get to the yellows, you have to hit your second button. So second E. Oops, I got to turn mine on. So clear this off. No, not that. Second, and I'm going to do my E again. And I just want to see what it equals. It's about 2.718281828. This is rounded, okay? It actually doesn't repeat and it doesn't end. It's an irrational number, okay? E. And it shows up in a lot of financial applications. All right, the definition is 1 plus 1 over n to the n power as you take n to infinity. You may not know what this limit notation means, but it just means if you continue to do this, 1 plus 1 over n to the nth power. So let's pick a really big value for n. Let's do, let's just try 100. All right, and put it in our calculator. All right, so we know what E equals. So let's try it here, 1 plus, and we'll try 1 over 100. Divided by 100. Then it's raised to the same n, so raised to the 100th power. Now we get a pretty good approximation, but they say the bigger this gets, the better the approximation. 1 plus, all right, let's do 1 divided by 1,000, but you got to raise it to that same power, raised to 1,000. All right, see how our approximation is getting better and better. So the bigger as this value right here, and it's repeated 2 times, as it gets to infinity, our approximation of E will get better and better. That's what the limit means. All right, so if we graph E, it is an exponential function with a specific base. The base is 2.7, blah, blah, blah. And if you, it's greater than 1, right? So it's going to go up left to right. And if you put it in, you have to really approximate it. So e to the 0 power is 1, but e to the first is just e, which is approximated 2.72, and you get a graph that looks like this. And you can also pick it up and transform it. So if I took the regular graph of f of x equal to e to the x, the basic one would be e to the x. All right, this negative in front of it, that's when you flip it over the x-axis. That's a reflection over the x-axis. The +2 up here with the x, this is where it goes horizontal, the opposite of what you think. You might think it would go right to, it's actually going to go left to. All right, so let's take the basic e to the x function. We're going to flip it across the x-axis, and then we're going to move it left 2 units. So you were at 0, -1. Now you'll be at -2, -1 once you move left 2. So transformations work the same way. All righty. And so that's it for this lesson. And let's see if I can find my keyword was exponential growth. And we see exponential growth a lot in business functions, and that's why you'll see the E value show up in business applications. All right, so email me your keyword, exponential growth. See you later.